This one, let's talk about the definition of a determinant using permutations and signs and so on. I definitely recommend to know some basics regarding permutations, their notation, like Sn, meaning the permutation on n letters. It's also a group. In that direction, we don't necessarily have to go that much, except we'll mention cycle notation to give it full context a bit. But let's talk about the definition of a determinant. So for example, you have, not for example just, but if you have an n by n matrix, we can define the determinant on it. So we have some matrix over the field F, so some field we choose. That means the entries are taken from that field. It's a square matrix, then we can define a determinant. Determinant is defined like this. We basically go through the group of symmetries or the set of permutations, and we take the sign of the permutation, and then we take the product that these products will basically add it up, including the sign which either makes these each terms minus or plus sign. This whole sum is actually equal to the determinant. So this is the way determinant of a square matrix is defined. So let's write it out. We basically get the following. We get then a multiplication. The A denotes a concrete term of the matrix. So we go like this, times, we multiply until A sub pi is a permutation from the permutations that n letters have. So that's going to be n factorial options. So it's going to be a sum over n factorial things until p of n. Well, this is just the coordinates of a concrete entry in the matrix. So let's now also generalize or concretely mention this thing. That is, we have a determinant of matrix A. Let's just make it more clear what we mean. So by matrix A, we mean we're going to denote it like this. It's going to be n by n, so n rows, n columns. This will be the number of the row, this number of the columns when we locate a concrete entry in the matrix. So we have, for example, a 3 by 3 matrix. Then this one is A sub 1, 1, the first row and first column, going from up to down and from left to right. So the first number is the row number, second is the column. This one will be A3, 3. In the case of n by n, it's A sub nn. This would be A1, 3, because this is the first row still, but the third column from the left to the right. So that's the idea. So in general, we have the terms being like this. The matrix. And now if we want to calculate the determinant, basically we have to take into account all the entries, and we always take a product that works in the following way. We go kind of from the left to the right. We can look at it on columns. We take from each column one entry, such that we multiply one entry each from each column, but always not from the same row twice. So for a 3 by 3 matrix, that would mean we have 9 entries. So we can choose this, 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 or we can choose this, 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 or we can choose this, 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 and so on, but not in the same row. So we take 3 entries, not in the same row. And the way we number them, well, when we actually look at the indexes, there's a pattern that arises. So for a good example, we can concretize it with 3 by 3. What this really means is we have these 9 entries. So we have A13, A11, A12, A13, A21, A22, A23, A31, A32, A33. So we have 9 entries for a 3 by 3 matrix, of course. So this is an example. And this example gives us a chance to look at it concretely. As I said, this is defined for any how big n by n matrices over a certain field, a determinant, but the way one calculates them is one can go from the left to the right like this, take from each row one element, one entry, and then multiply them the way you took them. So we are going to take into account, for example, this product, of course. We're going to take into account a product of these 3, like this, So the products we take are always 3 terms in a product such that they're not in the same row from the same matrix. So by permutations, which this is directly tied to, there is, for a 3 by 3 matrix, 3 factorial such products of 3 terms from this matrix, such that they're not in the same row and they're from different columns. So this directly ties to permutations, and when we notice, what we notice is when we go from the left to right and we choose the entries as I showed, we will end up with a sequence of 3 entries always, and it will always look like this. Something like A something 1 times A something 2 times A something 3. So at the second place, where is the column, because we go from the first to the second to the third column, these numbers are always 1, 2, 3. But these first numbers of the 2 in the subindex that contains 2 digits, that will differentiate them. And namely, when we write a permutation, we have, in this case, it's a 3 by 3 matrix, so we will relate it to 1, 2, 3 permutations on 3 letters. So these 3 things will go down here. So what we get is, let's write out the products concretely here. How many products do we have? As I said, 3 factorial. So case of 3 by 3 matrix, so dimension of this example. Well, let's take all the possible products. There will be 3 factorial, meaning 6, as I mentioned, so there's always n factorial of these products. And why do we care about them as permutations? Well, we will add these products, but when adding them, we either add them positively or as with a minus sign. So that would, of course, differentiate the result. That's how determinant is defined, because this SGN, sign of pi, it means the sign of the permutation. The sign of permutation is a particular thing. Each permutation has either a plus or minus, which I'll tell you in a second how to find out. But first, we just need the products themselves. And then later, all we have to add is either a plus or minus between them, and then the result is the result, the value of the determinant directly. So let's write out the products first. We have A11, and then we can multiply by the entries in different rows and different columns, such that they're not in the same row. So A11, A22, A11 times A22 times A33 works out. For starting with A11, we have one more option, that's A11 times A32 times A13. Then we can just list it A21, or let's now do A31, for example. So A31 times A22 times A13. Then A31 times, which one we have left? A12 times A23. And let's start with A21 times A12 times A33, and A21 times A32 times A13. So we have 6 products. And now either we put a plus or a minus sign in front of them, then we add all of it to directly correlate to this definition of determinant. That's what it is. This part is the products that we listed now. We have n equaling 3 now. But as we see, this thing will differentiate. That's what differentiates them. That's why we have the sum, we add them up later. And this sign, all it is a plus or a minus, the output of this. So behind each of these, we can find the corresponding permutation. Namely, for the first one, the permutation is going to be always, the first row is the column sequence, which is always same. We can see 1, 2, 3, 1, 2, 3, always same in all 6 listed. So the first row here is always 1, 2, 3. Second row, the permutation, the second row of the permutation. And this is also why it's important. I said it's important to know permutations, perhaps before going to this topic, because it helps a lot. So we don't have to go back and explaining every single thing. And that is the first entry here, 1, 2, 3, is the second row. So it means 1 is sent to 1, 2 is sent to 2, 3 is sent to 3. That's what this notation means. And we can write it also in so-called cycle notation. Although this first term is not a good example to show cycle notation, because it's the most trivial case where nothing is moved. 1 stays at 1, 2 stays at 2, 3 stays at 3. That's very trivial case. So that would be confusing to explain or remind one of cycle notation by. Okay, And for each of them, we do the same. So for the second one, again, the first row will be 1, 2, 3. And the second row is the first entries. So 1, 3, 1, 1, 3, 1. We can directly translate these into a more compact sort of so-called cycle notation, which I just mentioned. That is, we just locate where the numbers are moved. If we drew it as directed graphs, we would sort of have cycles that are separate from each other. So what do we get? Here nothing is moved. 1 stays at 1, 2 stays at 2, 3 stays at 3. We could write it as 1, 2, 3. We put it in parentheses, the cycles, but there's nothing moved. So they're on their own in separate parentheses. Also, the order of them doesn't matter. Because also in cycle notation, there's something called reduced form, which is very common. That means we don't even write the one-term cycles. So this is like identity. We can denote it actually ID of the ID 3. Of a permutation on 3 letters, the identity permutation. It moves them not. 1, 2, 3, move to 3, 1, 3, 1. So 1 is not moved. So we can write 1 in its own parentheses. 2 goes to 3, and 3 goes to 1. So what we do is 2. Oh, this is a mistake. This is 2. That doesn't make sense. We cannot have them repeated like this. If 1 went to 1, it cannot go, 3 cannot go to 1. So this was 2. Let's just check it. Was it 2? 1, 3, 2. Yes, so it's going to 2. So 1 goes to 1, that doesn't move. But then we have 2 goes to 3, and 3 goes back to 2 here. So we write like this. The way we read cycles is we go from the left to the right, and when we end at the last one, there's just 2 here, we go back to the first one. So it's 2, 3, or 3 to 2 is the same, equivalent notation. And we don't have that much space. So instead of doing this again and again, let's try to write it on the left side. And write out the permutations that correspond to each of these products we wrote out. So we have this product will have its own permutation. So this one has identity permutation, no change. We can just say ID, not too complicated. Or we could do ID sub 3 because it's 3 letters, that's why. Then A11, A32, A23, the second row, we only care about what does this give us. 1, 2, 3 going to 1, 3, 2, we just did it. So that gave us the 2, 3 or 3, 2, that's equivalent to say, that's the same. This one, again, the second ones are same 1, 2, 3, but we care about the first ones and put them in the second row of that table notation. So 1, 2, 3 goes to 3 to 1. That means 1 takes to 3, 3 goes to 1, and 2 stays. So we can write it as 1, 3 or 3, 1, the same. And 2 would be on its own like this. But as I said, by convention, the ones that are on their own can be like removed from the string, from the array of cycles. And then let's go to the remaining 3. So 1, 2, 3 is the same, 1, 2, 3 is the same, 1, 2, 3 is the same. We take care of the first number of the 2 in the subindex. So we have 3, 1, 2. So what does this do? 1 goes to 3, 3 goes to 2, and 2 goes to 1. So all are moving somehow. So we have 1 goes to 3, 3 goes to 2, and 2 goes to 1. So we actually now have a 3 cycle. So that's different. That's the first time we see that, in case you didn't have exposure to 3 cycles before. And now A21, A12, A33. Well, it's 2, 1, 3 now. So this one is not moved, but 1, 2 is moved. So the same like 2, 1. And the last one, so that corresponds to this one. And this one, we have 1, 2, 3 going to 2, 3, 1. So that is 1 to 2, 2 to 3, 3 to 1. So it's 1, 2, 3, a 3 cycle, so-called. And now we need to use these cycles, that cycle notation for permutations. So we have to construct all this stuff, and that's why I recommend to know this. And that's why I would expect maybe some of you guys have skipped to this part to skip the reminder of how permutations are denoted as with this cycle notation. Now we need to know the sign, because the sign will tell us in this sum, do we put a plus or minus for each of these terms that has the product of three entries from the original matrix. Well, identity permutation is even, this is odd, and the reason is, well, there's something called the sign of a permutation. So again, this is worth, of course, explaining, not just mentioning. So the sign of a permutation basically is the number of even cycles in the permutation in cycle notation. ID, what it does, ID sub 3, it does, there's no even cycles, there's just no cycles at all, there's 0 even cycles. Even cycles means the cycles of even number of numbers in them. So this has 2 numbers, so there's an even cycle, this is an even cycle, there's 1 even cycle. That's why these 2 cycles on their own, because the whole permutation is denoted by this 1-2 cycle, 1 even cycle. That means there's an even number 1, even number of even cycles. Then therefore the sign, which I'll write in the most left column, is going to be minus for these 2 cycles, because there's 1 of them. If there was another one that of 2 numbers, then it would be an even permutation, because it would have 2, therefore an even number of even cycles. But let's start with the first one. So the identity has 0 even cycles. 0 is seen as even, so this has a plus sign. Plus means we will put a plus in front this product. Actually, the official output of the function for the product in the definition to work out is +1 or -1. So we can say +1 is the sign. So let's actually put it in a proper column. So this is +1. 3, 2, again, even versus odd. So output of signum, which is this, where if it's even or odd permutation, if it's even, it's +1, if it's odd, it's -1, depends on the number of even cycles. Well, there's 1 even cycle. That means that's an even number. There's 1 even cycle. It means there's an odd number of even cycles. Odd number of even cycles by the signum function implies -1 as output under the signum function. So this permutation is called even. The same goes for this one, also an even number of odd number of even cycles. This one, there's 0 even cycles, and furthermore, there's actually this theorem. This 3 cycle can be written as 1, 2, 1, 3. So there's 2 even cycles, or we can look at it 1 odd cycle and 0 even ones. So it's actually this was minus, but this is plus, because a free cycle on its own, it's 1 odd cycle, but it doesn't matter. Let's count how many even cycles there are. That's what gives us the answer to the sign of the permutation. There's 0 even cycles. That means an even number of them. That means it's +1. 2, 1 is the same case like with the two cycles before. So it's -1. This one is the same like the 2 permutations ago, +1. So as we see, there's the same number of odd and even permutations. Like here, we see there's 3 odd permutations and 3 even permutations. And so for all of these products, we add them up according to this definition. That is this, and either put a minus or a plus in front of them when adding them up. So the determinant of a 3x3 matrix is basically defined this way. Determinant of a matrix that 3x3 is the addition of these, and we have to put the proper sign. So the first row product is this one. We just put a plus in front of it because we multiply by 1. So we actually add them, but we either multiply them by +1 or -1. That's what causes the signs between them. The first one we saw, it's identity permutation, it's an even one, so it's a plus. Then the second one we subtract, the second row. The third one we also subtract. We have minus A31 times A22, A13. The fourth one we add, because it's a even one, we go to plus 1, A31, A12, A23. Minus is the before the last one. We have a negative sign there. And the last one we add. All right, so great, that's what we wanted. So this was the example for a 3x3 matrix. And the generalized case is, of course, the formula we had right in the beginning, which we could also just reinterpret in a little bit easier fashion if we want to really minimize the notation. Let's take some matrix n by n over some field f. Determinant of the matrix is going to be the exact same thing, but what it really means is we just always need to write all the products. So it wouldn't be products of 3 elements, but it would be n added products of 3 entries each, and factorial added products of 3 entries each, because for 3 by 3 it was 6 terms for which each of them we had to find out is a plus or minus. With each having a plus or minus based on sign of its permutation, corresponding permutation. So we can denote this as the set element pi from the sets S sub n. So if the permutation is even, it will have a plus sign in the sum. If it's an even odd permutation, it will have a minus sign. And it works the same way. Just these strings in these products will always have the number of entries as there are columns, which of course we take into determinant square matrices, which is the same as the number of rows. So the n by n determines there will be n entry long products for which each of them we have to find out whether it's corresponding permutation, which is denoted by the first of its 2 entry subindex. These numbers basically, when you write them as a permutation, so it's 1 until n, and then it's this is denoted as pi of 1 until pi of n, because the permutation just assigns, it's a bijection, and it assigns these numbers 1 to n the corresponding thing depending on the permutation. In this case, nothing changed. It would be 1, 2, 3, 1 until n here, but in here it would already be slightly changed. And of course, with rising n, the complexity of these permutations rises as well.